So welcome all of you to the Uplift Final Conference. The title for this workshop is Shaping Tomorrow's Packaging Today. This project started like 4 years ago. I'm so honored to be moderating this webinar because I started basically at Sustainable Innovation with this project. So we are, let me move. So we are here to discuss and to showcase to all of you the different outcomes that during these 4 years the consortium has been working on the different upcycling plastic topics. So I will briefly introduce the agenda and then I will give the opportunity to the speakers to make a super quick introduction round. So we have started now. The first topic will be the plastic biorefinery concept explained by our project coordinator, Cristiano Barone from the Aalborg University. Then we will jump to the plastic value chain analysis. This topic will be explained by Alberto Barranca from AIM+, and then we will move to Felice Quartinello's speech, which will be revolving around the polymerisation of plastics and cleaning. Then I will give the floor to Tanya Narancic to talk about fermentation of building blocks, and then we will have a short break of 10 minutes, approximately at 10:20. Then we will restart the webinar with the Anders presentation about chemo-enzymatic polyester synthesis. Then we will move to Georgios Murgas from Tecnaro to talk about the scale-up and manufacturing task that has been produced in the Uplift project. And we will finalize with the Pablo Ariño Aguilar's presentation about recycling the plastic packaging industry. Then we will have like final conclusions and we can answer all of your questions there or all the questions that maybe we didn't have time during the speaker's presentation. So as I said, let's before introduce all of the speakers, I would like to let you know that this session is being recorded. Then make sure, this is especially for the speakers, make sure your microphone is muted during the other speakers' presentation to ensure that the audio quality is correct. And then we want to make this final event as much interactive as possible. So all the attendees that are here today with us, please, I encourage you to use the chat function and enter all the different questions you may have during the presentation of the speakers. So in that way, we can have a more dynamic session and answer all your questions. So moving to the speakers, my name is Pablo Morales. As I said in the beginning, I'm the Communication and Dissemination Manager for the Uplift project. And I'm so honored to be moderating this webinar because, as I said, this was my first project and I'm very glad to finish it from the very beginning. The project had a duration of 4 years. February is the last, officially last month. So here my role has been to promote all the partners' contribution and outcomes and make all the result, disseminate all the different results through different channels, online, but also offline. So part of the activities is to organize this final event. But now I think it's time to give the floor to Cristiano Barrone, who is our project coordinator. So Cristiano, quick and short introduction of yourself, please.
Thank you, Pablo. And good morning and welcome also from my side. So as already mentioned, my name is Cristiano Barrone. I'm Associate Professor in Fermentation and Bioprocess Technology at the Aalborg University in Denmark, and had the pleasure to be coordinating the Uplift project for the last 4 years. And I'm also leading a group dedicated to plastic bio-upcycling and plastic biorefineries here at the Aalborg University. So in the Uplift project, we also contributed with some research dedicated both to enzymatic depolymerisation of plastics, but also then microbial upcycling into new polymers.
Thank you so much. Then I think we can jump to Alberto Barranca from AIM+.
Hi, Pablo. Hi, everyone. Well, I'm Alberto Barranca. I am the World Package 1 leader. The same than Pablo, this is my first project to the beginning to the end. So also I'm very glad to finish in the Uplift project. Well, I belong to AIM+, the Plastic Technological Center. We are based in Spain, in Valencia. And well, I will introduce to you the main aspect relative to the Work Package 1, relative to the plastic value analysis. So thank you.
Thank you, Alberto. Let's continue with Felice Guartinello from ICIF.
Yeah. Good morning, everyone. So Felice Guartinello here, Work Package 2 leader, and my research topic is just like evolving into enzymatic processing of different kind of waste streams valorization towards like either valorization and upcycling. And this is also why we are involved in the Work Package 2, where we have the depolymerisation processes and later just like the purification of the project.
Thank you so much, Felice. Then let's jump to Tanya.
Now, I will wish you good morning as well. So my name is Tanya Narančić. I am teaching microbiology and biochemistry in University College Dublin, and my research is also related to biochemistry and microbiology. We like to understand microorganisms better so we can rewire them and make them more efficient at producing something that's of value for us. And that's exactly what we did in Uplift project along with Work Package 3 partners. And that's what I'll be telling you about later when I talk about the fermentation of building blocks.
Thank you, Tanya. Let's continue with Anders.
Good morning, everyone. I'm Anders Daugaard, and I am at DTU Chemical Engineering, where I have in this project acted as work package leader for Work Package 4, coordinating the polymer part and the polymer synthesis part.
Thank you. Georgios from Tecnaro.
Hello, everyone. Good morning to you. I'm Georgios Mourgas. I'm a researcher at Tecnaro GmbH. We were participating in the Work Package 6. Our main focus was the development of formulations, where we can go with the polymers, where we take from the previous work packages and transform them into industrial applications. I will give you a quick interview of that part on that work in Work Package 6. And yeah, that's from my side. Hello.
And last but not least, my name is Pablo Ariño, also from Sustainable Innovations.
Yes, hello, everyone. Good morning. I'm Pablo. I'm sharing with the moderator not only the name, but also the company we are representing. I'm business developer manager at Sustainable Innovations, and as well, I joined the company when the Uplift project started. So it's a pleasure to be here explaining and discussing about the different outcomes that has been produced during the Uplift project in the way not only about the technical results, but also how they have been captured in the white paper we have prepared, focusing on reshaping the plastic packaging industry. So good morning, everyone.
Great. So thank you, all of you. I think now it's time to start with the Cristiano's presentation. So if it's easier for you, Cristiano, you can share your own screen.
Yes, I will do that. Thank you, Pablo. Okay. So, morning again. And before we start digging into the science part and research results and the most relevant findings of the project, I would like to give you a general introduction about Uplift and about the plastic biorefinery concept, and try to explain a little bit better how the project can actually contribute to reducing or tackling some of the problems associated to the plastic waste. So, to better understand this, maybe we should start with some key facts about the plastic value chain and looking to the whole value chain. So how we're producing, using, and the...
Sorry,
Yes?
Christian, I think we cannot see your screen. I don't know if you have started. Yeah.
Yes, I was supposed to. I'll try again. Share. Can you see it now?
Yeah, put it in full screen.
All right. Thanks, Pablo. I hope this works better.
Now it works. Yes.
Thanks. Sorry for that. All right. So let's look a little bit at the plastic value chain, so how we're producing, using, and then also handling the waste at the end of its life. And so let's start with the way we're producing plastics. We can see that historically there has been an exponential growth in the production of plastic, 20-fold increase in the last 60 years. And predictions are that we will increase even further by 3-4 times by 2050. And out of the currently 460 million tons produced every year, actually 99% of this is obtained from fossil resources. And besides that, besides the very high amount of plastics and the growing amount of plastics that is produced, we're actually not particularly efficient in managing the end of life of this material. So if we take a look at the global plastic flow, we can see, first of all, that this is really still a linear value chain from production, use, and then disposal, which is particularly or sadly inefficient. I would say only 16% of the plastic is actually collected for recycling. There are some process losses. So in the end, we're actually on a global scale able to recycle only around 9%. And this has as a consequence that large amounts are actually not properly managed. They are largely landfilled or even leak into the environment, contributing to pollution, for instance, into the oceans. We know that currently we have more than 150 million tons floating around the oceans, and sadly also predictions foresee that there might be more plastic than fish in the sea by 2050. And we also know that around half of the plastic that we are currently using and disposing of actually has a lifetime of less than 1 year. But we know that plastics are designed to last very, very long. So there's probably a mismatch between the durability and the current application. How does it look for the future? If we look at the new OECD report from 2022, without going through all the complicated numbers here, the take-home message here is that basically if we don't change significantly the way we produce and manage plastics, then even by 2060 we will be still only recycling around 14%. Take-home message here, so we're producing large amounts and there are still large streams of plastic types that we're not really able to recycle. On top of that, we also know that around 8% of the overall fossil resources are currently used to produce the plastics, and probably will be around 20% by 2050. So 20% of all the fossil resources will be used only to produce plastics. So this clearly shows that we need to do something if we want to decouple plastic production and become maybe more renewable. So how can biotechnology contributes to this? In my view, I would say there are at least 2 key sectors where biotechnology can contribute. The first one is actually trying to reduce this dependency on fossil resources. So we could actually exploit, let's say, renewable biomass or renewable feedstocks and waste streams. And through fermentation technology, we will be able to produce high-value building blocks such as carboxylic acids, diols, or even just directly bioplastics. And this should give us then the chance to design for new materials that might be having, for instance, improved functionalities. Think, for instance, of PEF compared to PET. It will reduce greenhouse gas emissions thanks to the CO2 incorporation of the biomass, and hopefully decrease our dependency on fossil fuels. The other, let's say, pillar that I see relevant where biotechnology can contribute is also on, let's say, the recycling part. So we have seen some recent very promising developments. For instance, think about the Carbios process that is being scaled up right now, where enzymatic depolymerisation and then also maybe upcycling of the monomers can actually contribute to a more efficient recycling of certain streams that maybe currently are not properly recycled. So overall, the idea would be that we stop leaking and wasting plastic into the environment, start considering instead as a feedstock, as a valuable feedstock, as a new stream for a more circular plastic sector. This leads us to this plastic biorefinery concept, but what do we mean exactly with plastic biorefinery? Let's break it down in a very simple example. Maybe the most simple case that we can start with is PET, because it's a straightforward polymer just made of mainly two types of monomer, terephthalic acid called TPA and ethylene glycol, or EG. And if we imagine that we have an efficient process to depolymerize this PET into the building blocks, then we could, of course, recycle these, but we would still be working with fossil resources or non-renewable resources. So a possibility is actually to integrate this with bio-based fermented building blocks, for instance, glycerol fermentation to produce 1,3-propanediol, or lignocellulosic biomass that can be converted into furandic carboxylic acid. And combining these depolymerized plastic waste monomers with bio-based building blocks, we could obtain new, more carbon-neutral polymers that might have improved functionalities. An example here is polytrimethylene terephthalate, PTT, that is used in the textile sector quite a bit, or for instance, PEF, that is having these very promising properties and might be used for bottles, for instance, especially for fizzy drinks. So this was a bit the starting concept, but we wanted also to have a bit of an idea of if this concept is actually feasible, if you would imagine to scale this up. So we started with a simple theoretical calculation of techno-economical analysis based on large-scale technologies that are available already now. So we started with, for instance, the enzymatic depolymerisation of PET bottles based on the Carpus process and simulated that. We took the best fermentation process for glycerol to produce 1,3-propanediol and the best chemical conversion of waste of lignocellulosics into FDCA, and then calculated the mass and energies involved here to resynthesize all the monomers, so the ones from depolymerization of the plastic and the bio-based ones into the new polymers PTT and PEF. And we took a case scenario, for instance, what happens if we take all the PET available in Denmark. So we calculated the amounts involved. So we saw how many tons of cellulose we would need and how much of the glycerol, considering having 100,000 tons of PET, and how much PF and PTT we could obtain out of this. All right, but once this calculation is done, the question is, of course, but would this be economically viable? Would we actually be able to sell this on the market? So what we did was to take a look at what is the selling price, for instance, of PEF or PTT, and sorry for that, which is estimated to be around $4 to $5 per kilo. And then we tried to see, okay, how much would our process actually cost to synthesize these new materials from the waste streams that we mentioned. And maybe not surprisingly, we saw that if we take first generation biomass, so let's say sugars and glucose, we would have a minimum selling price of, let's say $2.3 per kilo. So this means that we could actually sell and make profit. And this would give a payback time of around 5 years. While if we take a waste stream, so second generation feedstock, the processes are way more complex, require more pretreatment. And this means that the selling price would be higher and basically the payback time would be way too long to be credible. But of course, we would like to develop a sustainable biorefinery that is not competing with food. So we tried to look into what should we do to make this second generation biorefinery more viable. So we tried to focus a little bit and see what is the most important bottleneck in this biorefinery process. And we saw that the most expensive part was actually associated to the production of the furandic carboxylic acid, both in terms of buying of the raw materials, but also the pretreatment and the energy associated to, for instance, high pressure and temperatures associated to the lignocellulosic biomass treatment. So this means that if we want to significantly reduce the bioplastic production here, we should somehow reduce the amount of feedstock that we use and the high energy intensive pretreatments. And how could we do that? One way was to look into the policies and the ambitions of the EU, where we know that basically in the coming years, the ambition is that we should increase the recycling rates to 55% by 2030. So we make several simulations. We know that our process would cost around 3.5 euros per kilo if there's no recycling. But if we increase the recycling rate, that would mean that we need less of this expensive anti-carboxylic acid to be produced because we're just recycling it. And what turns out is that we actually implement this 55% recycling rates, we will be able to decrease the production cost by 48%. And in this way, you obtain a cost of around $1.6 per kilo of plastic recycling. This could be comparable with current cost of rPET. So this might seem to make some sense. So this is what we were up to. This was the basic idea, but that's what we wanted to test. And to do this, we gathered a cross-disciplinary consortium of 15 partners, 8 different countries, and we tried to cover the whole value chain, the whole plastic value chain. So in this consortium, we had, for instance, plastic recyclers that were sending us the waste that they're not able to sort, and they're sending just for incineration. So that was our feedstock. We have universities and research institutions with expertise in biotechnology, with chemo-enzymatic depolymerisation, with microbial processes, and with synthetic biology. And then we have, for instance, the experts in polymer chemistry that will redesign new materials with improved recyclability, and also compounders that can make different formulations and produce new packaging materials. The plastic biorefinery that we developed in Uplift is, of course, a bit more complex than just the PT case that I showed you. So our starting point is this post-consumer mixed plastic waste that currently is not sorted and is just incinerated. And we applied chemo-enzymatic depolymerisation to break this down into building blocks, into the monomers, at least for the polyester part. And these monomers were then integrated either with bio-based building blocks or upcycled into new higher value products. So some examples was, for instance, this FDCA, different types of PHAs, and bio-based aromatic compounds, for instance. And then through eco-design, we obtained basically some new polymers that are easier to recycle. And through different formulations, we focused on mainly 3 big categories, so PHA and PLA copolymers, and also these PLA aromatic copolymers with new bio-based additives. And basically the best processes were then scaled up to TRL6. And we basically were able to produce different new packaging material involving both rigid trays, flexible films, and we made also some tests with bottles. So to conclude, our idea is basically that Uplift should contribute and become part of the recycling ecosystem, not only to complement mechanical and chemical recycling through biodegradation that then leads to biomass that then can be reused as building blocks. But what we would like to propose here is that we really integrate biotechnological recycling as a complementary technology within the already existing mechanical recycling and the newly developed chemical recycling, where we see that certain streams are particularly suitable for enzymatic depolymerization. And then we should definitely also use this technology as complementary where the other technologies are not as efficient. And then reuse the monomers or upcycle them with also combined with bio-based materials to make it more carbon neutral. And of course, the main idea is to finally improve also the recyclability and reduce the impact on the environment. This being said, I would like to thank you and give the word back to Pablo.
Thank you, Cristiano. We have a raised hand, but I would rather if the speaker, the attendee can enter the question in the chat. This is just for privacy issues, not because I don't want to give you the permission, but it's better if you enter the question so all the attendees can read it. So maybe we can go back with the speaker question later in order to not delay the duration of the webinar. So now it's time to jump to Alberto Barranca's presentation.
Thank you, Pablo. Can you hear me?
Yes.
Well, okay, thank you. So, well, I'm going to share my screen. Okay, can you watch the
Yes.
presentation?
Perfect.
Okay, thank you. So, well, I'm going to start this brief presentation about the Work Package 1 titled Plastic Value Chain Analysis. I have to say that this work package is an introductory work package to the technical work packages that which has been executed during the Uplift project. And I have divided this presentation into three main blocks. The first one is a general picture about what we have worked on this work package. Then we are going to jump to the main results that we have obtained, mainly in the standardization part, in order to finish with the block 3 about the main conclusions of this task. So this work package is divided into two main parts. The first one has been the preliminary analysis and standardization. So about this preliminary analysis, previous to the execution of the technical part, we have tried at the beginning of the project make like a map about what are the main the main challenges that has been to overcome during the execution of the work package of the technical work packages, mainly work package 2, work package 3, and in addition, work package 4. So apart from this preliminary process design or challenges identification, we have worked in a preliminary economical analysis. So we understand that this aspect is quite important, sure, in these novel recycling technologies. So with the market analysis that has been developed in the work package 1 led by sustainable innovation, we can get a nice peek about economical aspect and also the market picture about these new recycling technologies. In addition, we have worked in a Neswood analysis in order to trying to define what are the main strengths and opportunities, but also the main weaknesses and threats about these technologies. So this kind of analysis is quite important in order to identify possible gaps and in addition define plans in order to overcome the main weaknesses to mature these new or novel recycling technologies. So finally, in the phase 3, I have to say that we are currently working in progress in order to finish this part. We have worked very deep in the standardization part in order to analyze the current, not only national, but also European context. So it has been very important, the feedback of the different partners in order to study and know more about the normative and the legal framework close to the project. And in addition, we have worked not only very close with the partner of the Uplift consortium, but also with the sister project in order to develop a white paper that I will explain to you later, in order to aim to the public administration and also lead to the public administration to know about this kind of project which are in favor of novel recycling technologies of plastic. So this is the part one. This part one will be the focus of this presentation because my colleague from Sustainable Innovation will explain to you during the event more or deeper aspect about the market assessment report and the white paper that they have written about this aspect. So in a like an overview, okay, this market assessment has been divided into different phases. So the first one has been the target market identifications, and the second one has been the external market analysis. Also, they have developed the analysis of the market environment, and then the analysis of the market attractiveness with the Porter tool. But don't worry, because my colleague will explain to you more during the event. So I'm going to provide to you some keynotes about the research that we have collected during the part one about the preliminary analysis and the standardization task. So as I talked to you at the beginning of the project, we developed a document, a plan about with the collaboration of the different technical partners about the different challenges we have faced during the Uplift execution. For example, how will be developed the depolymerisation of polyester, what kind of depolymerisation strategies we are going to face during the project, or for example, we talk or we plan about what kind of microorganisms are going to be used during the Uplift project. So in this first or zero stage, it was defined this kind of questions in order to organize better the main challenges technical partners have faced on during the project. In addition, and in parallel with this preliminary analysis, it was developed and in a complementary way with the market analysis, it was developed like a preliminary economical plan in order mainly study what are the main factors that determine the price of recycled polymers, because this information is quite important if we want that the project, that the technologies studied not stop in Uplift, but also continue in other project, and also continue in the way to reach the market level. Okay, so it was analyzed different factors that conditionate the price of the recycled polymers. For example, price of the building material. Also, it was analyzed the supply and the demand factors. In addition, it was defines the link between the prices and also the quality of the recycled polymer, or for example, the importance of the material specific requirements. So with this picture, we got like a general view about the importance of phase with this factor. So with this analysis and the previous analysis, we define the zero stage of the Uplift project previous to the real start of the technical work packages. During the Uplift project also, we developed, as I talked to you in the introduction, strengths, weaknesses, opportunities, and threats analysis in order to understand where, in what point we are, in this novel recycling, biological enzymatic recycling technologies. This SWOT analysis, it was like a previous stage to the next part that I hope that it will be developed later, maybe in other project. Regarding to the chemo analysis, the correct, adapt, maintain, and explore analysis. And here in this presentation, due to the tight timetable. I prefer to be optimistic, so I'm going to highlight some strengths and opportunities it was identified. I have to say that this study was not developed by myself, so it was quite important for this the feedback and the internal contribution of the different actors who belong to this project. I mean, the universities actors, also the research technological research center actor, in addition the industrial partner, because depending on this, they have one view or another about the maturity and the development of this kind of technology. So, for example, regarding the strengths, as Cristiano has talked to you in the introductory presentation, this project fits very well with the biorefinery concept. So this aims to address the scale up to the market level. And for example, as also it has been explained, no high energy or equipment high cost required. So this easy the maturity of the maturity level of this technology, or for example, no toxic chemical are required. So this is very in line with the new or the current European policies about environment sustainability. So this, for example, also I want to highlight that one of the main economical advantages of the Uplift technologies is to take part of a niche market, I mean, to the biodegradable and recyclable packaging. So this strengths and other opportunities, like for example, the integration of the Uplift technology with other existing recycling technologies, or the capability of obtaining different ecopolymer with different properties. So the strengths and the opportunities that has the Uplift technology aim to reach more maturity of this technology, and we hope reach in the future the market level. So in addition, we work in a really important part. This is also quite in line with the white paper that I introduced to you. In order to make different recommendations for policymakers, I mean, this part is quite important because the legislation, as you know, and also the regulatory framework is modified with in this case, for the European administrations. So it's quite important to that these administrations get information about these novel technologies. They must to know more about where are these technologies, in order to know what are the gaps that avoid the development of the novel recycling technologies as has been executed in a Uplift. So we have tried to be like a driver, okay, for transmit this information to the European administration. So information regarding the necessity to incentivize support in a financial way topics relative to the recycling, biological, enzymatic, novel recycling technologies, in order to complement the traditional mechanical recycling, for example. Also, the necessity to establish a solid legislative and regulatory framework for these novel recycling technologies. For example, I think that a really good example has been the food contact plastic legislative framework that it was presented in 2022, in which it is open novel recycling technologies. So these kind of actions determined by the European administration aim to continue in working in the maturity of these novel technologies, recycling technologies, or for example, make more dissemination strategies in a social way in order to expand the knowledge of this novel recycling strategy. And here, as I talk to you, not only the internal work has been important, but also the joint work with the sister project. These sister projects are Uplift and Preserve. And why? Because they are different, but like a background, they are the same because they work or they have the same objective, okay, in trying to impulse novel recycling technologies. So we have worked during the project execution. In the white paper, you can see in the slide a screenshot, and you have obviously open access to this, in which it was explained to the European administration mainly. I think that is the main receptor. It was explained where we are, okay, and what are the main challenges that these technologies has to overcome from different point of view, for example, in the legal aspect, in the economical aspect, etc., in order to identify the main gaps that we have to overcome in the next years. Okay, so finally, I think that this is the last part of the presentation. In the phase 3, we have worked in a more internal way in the Uplift project, in the normative and also in the legislative framework. So it has been very important to start with the feedback of our European partners, okay, and know more about the legislation and the normative framework in different fields that we consider are very close to the Uplift development. For example, I mean in the eco-labeling, process traceability and material balance of processes, bio-based product, or food contact. So we work with this partner with a different questionnaire, and we compile different the different answers, okay, and we have make like a folder with this information in order to compile the main frameworks, okay, and this material permit to us to detect what are the main gaps that we have to face during the next years in the legislative field. So this was like a zero stage at the beginning of the project. And during the execution, also we collaborate so much with the booster department from in order to work in the standardization part. And in addition, we have been working in trying to identify in the Uplift project what are the main aspects that the technical partner consider should be standardized. So currently at the end of the project, when the most part of the most technical part has been concluded, we are working on this part in trying to identify possible aspect in the different processes in that belief project, what could be the point that we could standardize. So this will be the also like a zero stage in the normalization route. So here are some conclusions, but I think that I have talked to you the main information during the presentation. So, conclusion, I want to highlight the need of support for the European administration in terms of legal and also normative fields. And also it's quite important to need the necessity of define a novel concept that has emerged from this novel biological and enzymatic recycling technologies in order to make a solid legal and normative framework that impulse this kind of recycling technologies, and also, for example, trying to advance in aspect like the minimum recycling context. So trying to impulse, for example, the mass balance approach of these new recycling technologies, or for example, aim to companies to implement this kind of technologies, for example, including new recycling deduction or new recycling for tax deduction purpose. So I think that that is the main aspect that I wanted to share with you. So thank you very much, and feel free to ask whatever you consider.
Thank you so much, Alberto. So I've been checking the questions on the chat, but it seems we have a very shy audience, so we don't have question until now. So let's keep the webinar, and I keep encouraging the audience to make any questions that you may have during the speaker's presentation. I think now it's time to the next speaker, Felice, if you want to share your screen.
Can you see it?
It's loading.
Okay. Can you see it now?
Yes, perfect.
Perfect. So, hi again. Good morning to everyone. I'm Felice Quartinello from Azip Group, and today I will show you the, let's say, the summary of the most intensive results from the last period of Uplift. Just before to mention Work Package 2, so just small description of AZIP. AZIP stands for Austrian Center of Industrial Biotechnology. We are located in Austria, to be precise, in Thun, and we are expert together with Professor Kubitz in enzyme production, polymer science, and synthetic polymers processing. We are involved in many projects, EU project level, national projects, and also company. In package 2, as already previously described by Professor Varrone, we are mostly focusing on the chemo-enzymatic depolymerisation of different polyesters, either model substrate and real plastic waste into their monomers. Today, we also focus on improving and the last technologies that we are developing in Uplift, but as well the recovery of the monomer that we are obtaining after the enzymatic process and the hydrolysis of the eco-design polymers that were designed during the last part of Uplift. As previously mentioned from Professor Varrone, the enzymes has the role to depolymerize the polyester, like PET, for instance, into different monomers. If we think about enzyme production, normally it's coming from intracellular activities. Therefore, these require different kind of like methodologies to purify the enzymes. In the last part, especially this part was driven by the group of Aalborg, so Professor Varrone and his group. The idea was just to produce enzymes that were extracellularly secreted by the microbial organism, in this case Bacillus subtilis, and therefore, let's say, skip almost the full purification setup. In this case, like we can see that different kind of beta-hydrolases were just used to be produced and then defined by characterization in terms of like protein concentration, and then of course their own activity in terms of like PET weight loss efficiency. So we can see that, for example, there is like a good opportunity where some enzymes like LCC can be used as almost semi-purified enzymes directed towards polyester degradation. Still from the Aalborg University group, we don't focus only on the conventional plastics, but also into the let's say, outlook plastics like PEF, as previously mentioned, Professor Favarone. So like where the same enzymes that could degrade PET also can be used for degrading futuristic plastic, let's say. In this case, there was a work between Aalborg University and the University of Genova, specifically with Professor Pellis, where they define PEF degradation and also like the behavior and different kind of compounds that can be produced during the enzymatic approach. Specifically, they found out that using the high CCG enzymes, which is a variant of LCC, they managed to produce 4-decarboxylic acid, the dimers, MF, and then FFF, which is the trimer. The second group still in the task 2.1, which is like the optimization of the process, there was Lund University, which was driving the possibility to find out other cuteinases or polyester hydrolysis enzymes in order to be used for either degradation of other polyester, in this case, which was PBAT, which is like a semi-aromatic aliphatic polyester. And in this case, they just use their own cutinase produced by Lund University, where they managed not only to fully depolymerize PBAT, but also they managed to separe the monomers that were like compounding PBAT, namely adipic acid, terephthalic, and butanediol, increasing by the time the yield. We just saw during the progress of the uplift that the mass like was changing from 15 to 50 gram per liter of polyester, including in the reactor. Still from Lund, because we have the formation of chimeric enzymes. We know that sometimes the enzymes might have might need optimization process. So therefore, the idea of Lund University group was just to bind two enzymes by a linker, and therefore create these so-called chimeric enzymes, which basically they are improving the enzymatic approach. In their own work, basically they provide us in Uplift different kind of chimeric enzymes and compared with LCC, which is the same enzyme that is using in Carbios process. Therefore, we can easily see in this graph that we found out that one chimera enzymes has the same properties or sometimes higher than LCC itself. Not only was just tested with model substrates, so like monomaterial like PET or PBAT, but also from the mixed plastic waste that we got from Main Plus, which is kind of giving us a more realistic situation about polyester degradation than just using model substrate. During Uplift, we didn't focus also in Work Package 2 in Uplift, we didn't always focus on enzymatic approach, but also into chemo-hydrolysis. So with the group from Haken University, basically we developed different processes based on zinc guanidine catalyst for a specific degradation of PLA. In this case, they just tested various size or various structure of their own catalyst in order to perform ethanolysis of PLA. And not only they found out that it was pure or was fine to do it, but also they managed to recycle different times their own catalyst, still in the vision of optimization of the process, so potentially reducing the cost. As well, they managed to produce a scale-up of their own process, reaching the 175 gram of PLA degradation using mild conditions. But as well, they had also different kind of catalysts which when used for complete depolymerisation also in solvent-free reactions. In moving in task 2.2, we were mainly focused on the degradation of mixed plastic waste. These mixed plastic waste were given by our project partner, which is AIM+, and it was kind of defined that from their own selection, 2 were selected for further optimization process. And therefore, we just focus on these 2, where, in first instance, AZIP, so our group, was producing larger amount of hydrolysate. If we consider the enzymatic conditions, there was like in our case, our enzyme is using a higher concentration of buffer, which is like for later steps in Uplift might be not really suitable. So therefore, ATSIP, together with the University of Dublin, we were just like collaborating in order to perform a screening where different kind of buffer with lower concentration was used, and also different buffer like sodium phosphate, potassium phosphate, and trace buffer, in order to define the combination of which buffer and enzymatic activity might be suitable for later production of biopolymer, namely PHP. These actually from our side were sent in two versions to Dublin group. In a form, we just sent a full actualizate where TPA and ethylene glycol were present, and in other form, where just like only ethylene glycol were just like provided to them. Still speaking about the polymerization of plant material, real plastic waste, the Haken group, where we have this guanidine catalyst, were able to perform degradation of real plastic waste into HEMAT or BHET, which was then used for resynthesized polyesters. So therefore, this was also a collaboration that we had, or they had within Haken Group and DTU, where, like, for example, one publication has been submitted already. Still in Uplift, our process, our idea was just to optimize the enzymatic process, which we were able to do from the beginning, but as well just to give an eye on, let's say, fundamental research, where we need to search for new enzymes. In this case, like we had the idea just to find out which enzymes might be involved into polyester hydrolysis from a plant species, which was a carnivore species. Luckily, we just managed to provide some data by HPLC analysis, proteomic, and surface analysis, where we managed to find out how these enzymes present in these peach plants, is Nepenthes species, can be able to depolymerize PET and PBAT as monomaterial, and therefore we were able to isolate one enzyme that can be involved in this process. You can see that, for example, from the SEM analysis, also there is like a good pattern of hydrolysis on the surface of PBAT, for example. When we spoke about the degradation process, also as mentioned in the first presentation, we need to somehow separate or purify the monomers. So this was the main focus of the downstream process, which was performed in 2.4, task 2.4. This was a synergistic action between the group of ATSIP, Lund, Haken, and Halborg, where different kind of monomers were then separated. Specifically, for example, for PET, we were able to produce pure terephthalic acid after acidification process, which was then provided to DTU University in one package 4 for oligomers or polymer synthesis, but as well it is hydrolysate in different shapes, as I previously mentioned, were provided in work package 3. As well, not only after the enzymatic process, but also after the chemical process, we found out that, for example, PLA, which unluckily is a bit recalcitrant about enzymatic approach, this was eventually good depolymerized and selectively depolymerized from the guanidine catalyst from Haken Group. Specifically, they were able to selectively depolymerize PLA out of different mixture, where, for example, PET was present, or PCl was present, or PBAT2. So therefore, if, for example, if we think we have a mixed plastic waste where PLA is one of the components, in Uplift, we can just develop a method where only PLA will be degraded, leaving the others eventually to the enzymatic approach. Lately, in Uplift, we managed to, after delivering the monomers to DTU, so work package 4, eco-designed polymers were produced. So namely, we have in the first instance, we had PLA, which was like blended or copolymerized with PHPA, which is a monomer which was like producing web package 3. The next presentation will show the results. And then with different ratio of copolymerization between PLA, PHPA, then where just different films were created. And after enzymatic approach with fumicola insulate glutinase, like we just define which kind of like pattern of degradation we just found out. So we added either in terms of weight loss and HPLC. As I said before, PLA might be more recalcitrant to enzymatic approach, but we found out that using 3% of HPA, then the enzymatic hydrolysis was enhanced. So which means that the eco-designed polymer were actually better in terms of degradation than the pure PLA. Still, with the new eco-designed polymers, basically we had a copolymerization of PET and BCl. And as you can see from the picture, basically we can see that PET in presence of 3% of PHPA, we have a higher enhanced degradation profile. For PCl, we know that it's like a polyester that is easier to degrade it, but in presence of the copolymer, the degradation of PCl was even more enhanced. So therefore, this copolymerization, these eco-designed polymers were kind of like improving the degradation and enzymatic approach itself. Just something that needs to be mentioned, like within Uplift, we had different kind of enzymes, which every enzyme has its own optimal condition. So lately, group of Halburg, Hatzip, and Lund, we decide to standardize our process in order to measure or uniformly measure the enzymatic hydrolysis of these new eco-designed polymers, and these results might come, let's say, in the beginning of February. The eco-design polymer as well were tested under the guanidine catalyst, and here there was like strangely a beginning was strangely an opposite trend, where increasing the amount of PHPA, the degradation of PLA was decreased. But Haken group basically overcome this issue by increasing the temperature. So, and then reaching the temperature of 150 degrees Celsius, they managed to degrade fully the eco-design polymers into 1 hour time. As well as defined by standardization protocol, we need to define the biodegradability in terms of like compostability of our eco-designed polymers. Therefore, in this sense, the group from AIM Plus was stepping in and then performing the standard test for biodegradation process. In this case, like we can see that all the samples were reached 90% of the degradation or compostability compared to the standard reference, which was cellulose. And everything was detecting like almost 100% weight loss within 120 days, which means that also like our samples not only can be enzymatic degradable, but also they are compostable. If I go to wrap up a bit web package 2, basically we had the first part of Uplift where we just optimized the enzymatic approach, selecting different enzymes that might work in this direction. So we had the synergistic action of different groups, starting from AIM Plus, which was like our provider of material, with Halburg University, Hatzip, and Lund, where they were improving the enzymatic approach. Then we have ULI group, which was collaborating with Hatzip. I didn't put all the results because otherwise the presentation would be too long, but we were just like consolidating a two-step approach for polyester degradation. But also then we have Haken University with chemo-enzymatic approach. this led us to deliver, it's just to mention that Harvard University was collaborating with HKI, where they managed to increase also the production of enzymes, which like the upscaling process, it's really relevant for us, like in terms of like increasing also the amount of PET that can be degraded. But mainly the Work Package 2 was delivering a lot of like either hydrolysate and monomers to Work Package 3, and Work Package 4 in order to create different steps that were described in Uplift. Afterwards, in the last part, we had this backwards results where the DTU groups was the eco-design these polymers, and then again the enzymatic approach was stepping in, and the chemo-enzymatic approach was stepping in order to valorize our idea of biorefining approach, which was previously described in the first presentation. Not only like, of course, as like research, U projects, we participate in different conferences, like with the main topic of biotechnology, recycling, and polymer and biopolymers. We had a huge plethora of publications. Actually, it's written here that 2 were under review from ATIB, but it's nice to say that 1 from ATIB was accepted 2 days ago. So it's something that we need to change it. And last but not least, we have a patent submitted from Lund, which was filed the 7th of October, about the formation and application and the method how to create chimeric enzymes. As I said, like this is the last part of Uplift. The presentation would have been too long if I had to present all the results that we had in these years, but I hope everything was clear, and if there are any questions, I will be here to reply.
Thank you so much, Felice, and also for those dissemination contributions. I send in the chat the link where all the scientific publications are published on the Uplift website, so feel free to have a look there. Now it's time to move to Tanya's presentation. We can see your screen, Tanya, but we cannot hear you.
I didn't realize that I have to unmute myself before I share the presentation. Otherwise, I cannot find how to unmute myself. Okay, once again, hello from my side. I have seen that some people have joined after we actually introduced ourselves. So once again, my name is Tanya Narančić. I am from University College Dublin, and I'm also associated with a bioeconomy research centre called Bioorbic. So what do we do in University College Dublin? As the name suggests, we are located in Dublin, and you may think that it's always raining here, but from these images, I can show you that sometimes we get lovely weather. And in this university, we don't only teach students, we also have quite research intense community. And you see that we have about 2,000 academics that are performing research and a slightly higher number of postgraduate students. So what do we do when it comes to research? So this is a snapshot of research activities performed by myself and Kevin O'Connor, who's also a partner in the project. So we work with microorganisms, and as I said, when I first was introducing myself, we like to get to know our bacteria that we're working with, know them well, so we can improve them to produce better what we want them to produce, and also to be better at using feedstocks that are quite unconventional, including various feedstocks that are plastic feedstocks. For example, we have shown how hydrolytically or enzymatically depolymerized polyethylene terephthalate can be upcycled into valuable polymers, including polyhydroxyalkanoates. We have looked a lot into the metabolism of polyhydroxyalkanoates. So how are they produced? How is this production regulated? So we can kind of push our bacteria to produce more of them. One of the star bugs that we have used previously and continue to use in Uplift project is Pseudomonas umsogensis geo16. And the reason why we like this bug so much is not only that it can produce polyhydroxyl conates using, for example, monomers derived from polyethylene terephthalate, but it also produces simultaneously different types of polyhydroxyl conates and blend them together. I will not talk about in detail about this research that was done as part of Uplift, but if you want to read more about any of the work, you can find the links here. We have also looked at other non-conventional feedstocks. So we did use polyethylene terephthalate, as I mentioned, then mixed plastic waste that was pyrolyzed, and then we obtain a mixture of aromatic hydrocarbon that can be chemically modified into sodium benzoate that bugs really love, and use this to push the PHA production. And we also used carbon dioxide. So as you can see, the stars in all these different processes are microorganisms. So what we essentially do and what we did in work package 3 of Uplift project is microbial catalysis. I know the title of the talk is fermentation of building blocks. And when we talk about fermentation, it's not fermentation in strict sense. So it's not anaerobic growth and fermentative growth of microorganisms. We're talking about a process where we employ microorganisms to convert various feedstocks into various products. So what we rely on here is central carbon metabolism, where all these different feedstocks can be broken down and then using the building blocks to produce what's of value for us. So in Uplift, as Cristiano already explained, the feedstock that we were focusing on is mixed plastic waste. And Cristiano was already talking that, there are different ways to deal with plastic waste, recycling being a great kind of post-consumer management option for plastic, but we also know that there are so many different challenges. So in our line of work, we're focused on developing biotechnological processes that could take this mixed plastic waste and break it down into monomeric units that bacteria can digest and then use them to produce various products. In Uplift, the 3 kind of products that I would like to showcase here are, in general, aromatics, polyhydroxyl conates, and FDCA that, again, Cristiano talked about quite a bit. So in this work package that you see in this diagram is kind of nestled between the work package 2 that Felice was just describing, all the activities, and work package 4, where we were talking about creating novel ecopolymers. So what do we do? So we receive feedstock from work package 2, and you can see what different types of feedstocks that were produced in work package 2. And while these feedstocks or these molecules are valuable themselves and could be potentially be used directly to produce some novel polymers or just rebuild the polymers the same type that they were obtained from, in this work package, we wanted to give kind of new life to these plastics that are considered waste. So something that's of very low value, that's an issue. We want to use it to produce something that's of high value and that is potentially going to lead to the creation of novel packaging materials, which is the overarching aim of Uplift. As I mentioned, one of the products that we were focusing on were aromatics, and in particular, you will see that we focused on the production of 4-hydroxyphenyl acetate. Why aromatics? Well, these molecules are produced at very high volume from petrochemical resources, so obviously it would be very valuable if we can create a biotechnological process and produce them and then use them to design novel polymers. Polyhydroxyl conates are the second molecule of interest, and I would assume that a lot of audience here would know about polyhydroxyl conates, but I will give a brief overview of what they are. So these are biologically synthesized polymers. Bacteria use them as carbon and energy storage, but when you extract them from bacteria, they have properties that are similar to plastic. So we wanted to use petrochemical plastic as a feedstock to produce polyhydroxyl conates and use them to develop different blends that, again, could be used as packaging material. And finally, we also aimed at producing FDCA because, as Cristiano mentioned, FDCA is a monomer that's used for the production of polyethylene furanate. So another polyester very similar to polyethylene terephthalate, but apparently has better barrier properties and also is more susceptible to mechanical recycling. So what did we do? Again, I'm not going to, as Felice, showcase every single activity that we have performed in this work package, but I will focus and give you one example for each of these molecules. And I will start with the work that was performed by our partners in Jülich. And they focused on the production of aromatics. Which aromatics you can see they're highlighted here in purple. And these different aromatics, can be produced by an organism called Pseudomonas taiwanensis, or that was heavily engineered. So the starting premise of our partners in Jülich was not only to engineer Pseudomonas taiwanensis to produce these aromatics, but they were also thinking about that this organism will be used to produce these aromatics at scale. So they have used genome-reduced Pseudomonas taiwanensis that they have previously created that had certain features, removed from the genome that wouldn't be needed, or they could that could actually hinder the biotechnological process at scale. Then to produce these aromatics, they relied on shikimate pathway that's used for the production of aromatic amino acids such as tyrosine and phenylalanine. So in order to create push towards these aromatic amino acids, they have to kind of introduce several mutations and deletions in the shikimate pathway. For example, some point mutations that were, creating more efficient enzymes to produce more of these aromatic amino acids. And what then? When these aromatic amino acids have to be deaminated, and they would lead to the production of 4-coumarate, which is a valuable molecule itself, but also is a precursor for the production of other molecules. Simultaneously, Pseudomonas taiwanensis, like other Pseudomonas strains, can use some of the aromatic hydrocarbons, including 4-hydroxybenzoate. So if they wanted to produce 4-hydroxybenzoate, they had to remove the capacity of the organism to take them up, including using tyrosine and phenylalanine as form of carbon source. So once this is all removed and shikimate pathway was, flux through shikimate pathway was increased, then certain enzymes like phenylalanine, tyrosine ammonia lyases, and tyrosine ammonia lyases were implemented that deaminate tyrosine to produce coumarate. And then, as I mentioned, 4-hydroxyphenylacetate was one of the key molecules that we were targeting to produce within Uplift. And to do so, the partners in Jülich have implemented enzymes that are relevant for styrene metabolism. So styrene monoxygenase that was converted 4-coumarate into 4-hydroxyphenylacetate. So there was a strain that was now capable of producing this valuable compound. And within Jülich, they've done all the work at small-scale cultivation. So they've designed the strain. They've shown that the strain can produce 4-hydroxyphenylacetate. And then, as Cristiano was portraying in his talk, so we're trying to create a whole chain where we use something that starts from waste to produce something of value. And you can see here kind of this valuable process that's developed in Uplift, where ACIB has developed a process to enzymatically degrade drink package reject paper. So by enzymatic treatment, you get glucose, and glucose was then fed to heavily engineered Pseudomonas taiwanensis to produce 4-hydroxyphenylacetate. And this process was taken from the lab scale to the upscale process in HKI, another partner in our Uplift project, but also in Work Package 3. And they have scaled up the process at 30-liter scale, but also developed a downstream processing, so how to recover 4-hydroxyphenylacetate from the production medium. And then the process was further scaled up to 1,500 liters in bio-based Europe pilot plant. And you can see here kilograms of 4-hydroxyphenylacetic acid produced that was then used by our partners in work package 4 to create new polymers. And Anders will talk more about that. I did mention that another product that we were focusing on here were polyhydroxyalkanoates. And as I already mentioned, these are molecules that are produced by bacteria. You can see here bacteria, and you can see here big blobs that look like blobs, but they're actually accumulated polyhydroxyalkanoates. And around these bacteria, you can see different words that are used frequently to describe polyhydroxyalkanoates. So when you read literature, you will find all these different words, and some of them are correct, some of them are not so correct. But what I want you to see here in this kind of part is, or remember, is that polyhydroxyalkanoates are actually a family of polyesters. So it's not one molecule that's produced. You have a range of molecules that can be produced, but they're always polyesters. And we can roughly divide them into two categories: short chain length polyhydroxyalkanoates and medium chain length polyhydroxyalkanoates. And this is very important because the short chain length polyhydroxyalkanoates, once you extract them from bacteria, they will have properties that are different to medium chain length ones. So when you have short chain length PHA extracted, they look like polyethylene bag, but unlike polyethylene bag, if you put a little bit of stress to it, they will shear. Like, they're brittle, they're crystalline, so they will rip easily. And medium chain length polyhydroxyalkanoates, the longer the side chain is, more viscous they are. And you can imagine then by combining these properties, you can have a range of different applications. And by blending these polymers, you can get interesting applications that among them could be packaging as well. So we have previously demonstrated upcycling polyethylene terephthalate monomers obtained by enzymatic hydrolysis into polyhydroxyalkanoates, so I do not want to talk about that. But I will focus on recently published work where we used polyolefins to produce PHA. So you know that polyolefins, including polyethylene and polypropylene, are produced at a high level. So about 45% of annual plastic production goes towards polyolefins. And you would also know that these polyolefins are polymers that are made of carbon-carbon bonds. So unlike polyesters, you don't have bonds that are easily hydrolyzable by enzymes. So they're very recalcitrant to any attempt to biologically degrade them. But what we can do with these polyolefins, yes, we can recycle them, but then you have contaminated streams, and I believe that Cristiano was also talking about that, which makes it very hard to recycle them. However, if you pyrolyze polyolefins, you get a range of different products, and among them, polyolefin pyrolysis wax. And currently, there's only low-value application for polyolefin wax. However, if you take this polyolefin wax and kind of create a emulsion out of it, it can become a feedstock for bacteria. Not all bacteria will like polyolefin wax because it is made mainly from alkanes, from short chain to long chain alkanes, and long chain alkanes would be present in abundance there. However, in nature, there are organisms that can use their enzymes, including monoxygenases, dioxygenases, dehydrogenases, to convert these long-chain alkanes, to shorten them and convert them into fatty acids. So what our partners in Aalborg did, they took soil samples and did enrichment of these soil samples using polyolefin wax. To get the organisms that are capable of using polyolefins, polyolefin-derived alkanes as a sole carbon and energy substrate. So they have developed like 3 different consortia, and then looked at, once this consortia was enriched, looked at, which organisms are present there, but also what do they do with this wax? And they have seen that mainly wax is being converted as expected into fatty acids. And you can see here the composition of triacylglycerols, which would be esters of glycerol with fatty acids. And again, this now could become a very likable or amenable feedstock for a range of bacteria, including the ones that are producing polyhydroxyalkanates, because feeding fatty acids to PHA-producing bacteria is the best kind of way to get high titer of polyhydroxyalkanates. So one of the consortia was used to produce PHAs, and that was recently published. And if you want to read more about the process, and especially about design of experiments where we try to find optimal conditions, how much and how to feed this PO wax to produce PHA, you can find it here at this resource. But another thing that we did was, well, partners in Aalborg, they have isolated individual strains from consortia and then try to develop defined mixed consortia in order to produce more defined types of PHA. And hopefully this is going to be something that you're going to read about soon enough. And the third valuable molecule that we aim to produce is FDCA. And you may have been aware of various publications where different bugs or enzymes derived from different bugs were used to convert hydroxymethylfurfural that's derived from biomass. So when you have biomass and when it's treated, one of the side products is HMF. And because this is an aldehyde, it is going to be toxic to microorganisms. But I did mention a star of our research, Pseudomonas thomsonjensis Geo16, that we figured out can actually tolerate HMF, and not only tolerate it, but produce FDCA. So we looked into the pathway of HMF oxidation, and normally when HMF is used as a carbon and energy substrate, so for Geo16 to grow on HMF, it is going to be oxidized through a range of reactions, all the way to 2-ketoglutarate, which is one of the essential metabolic intermediates. And so it will lead to the production of energy and all the constituents of biomass. However, HMF oxidation goes via FDCA in Geo16. So we thought that if we delete genes that produce the enzymes that are involved in further FDCA conversion, we would be able to stop the through conversion and facilitate accumulation of FDCA. I have already mentioned that Geo16 was previously used to upcycle terephthalic acid and ethylene glycol, and this is the approach that we have employed here, where we use terephthalic acid alone or ethylene glycol alone, or the combination of the two, where we mimic the enzymatically hydrolyzed polyethylene terephthalate. And we obtain the biomass of Geo16, and then we use that biomass to convert HMF to FDCA. However, when we used our engineered strain to convert HMF to FDCA using terephthalic acid or ethylene glycol, you can see that there is quite a difference. So when terephthalic acid is used, you see the very low conversion of HMF into FDCA, and you see the byproduct formation or one of the intermediates, which is HMFCA. Ethylene glycol is a better substrate. When you combine the two, you see that there's kind of intermediate between the two solutions. And then we went further on and overexpressed the enzymes that are involved in all the steps involved for the HMF conversion into FDCA. And we got a much improved biocatalyst that can now completely convert HMF to FDCA using terephthalic acid as a secondary substrate, ethylene glycol, or in the case of mock hydrolysate, where we have both terephthalic acid and ethylene glycol, you can see that you get a complete conversion of HMF to FDCA within 12 hours of the biotransformation. So to sum it up, in work package 3, we have used feedstocks that came from work package 2 to develop biotechnological processes that are not meant as a replacement for current processes that are there for dealing with waste, but rather as synergistic solutions that are going to create a pool to maybe better collect and separate the waste and produce valuable compounds such as aromatic compounds, FDCA, and polyhydroxyalkanates. And with this, I would like to thank you for your attention, and I would be delighted to answer any questions you may have.
Thank you so much, Tanya. Perfect timing, actually. We do not have a question during your presentation. We have another one, but I think it will be better to answer at the end of the workshop. For now, I think it's a nice idea to take a short break of 10 minutes. So I just modified to start from now, and we can be back at 10:40. So see you in 10 minutes. Great. I hope you have enjoyed this short break. Now it's time to continue with Anders' presentation. Feel free, Anders, to share your screen.
I will do that. So you should be able to see the screen now.
Perfect. Yes, thank you.
Yes. So welcome everyone back from the break. I'll just move this. There we go. I have the task of presenting the work in Work Package 4, where I've been the work package leader. I come from DTU Chemical Engineering, where our group specializes in polymer synthesis. And this has also been the main topic of Work Package 4. So in the context of the project, we're now here in the middle of the scheme. So basically the task of Work Package 4 has been to work with the building blocks that has been produced from Work Package 2 and Work Package 3 through polyester synthesis, additive synthesis, design of new types of polymer compounds, and finally also through the fourth task in this work package to look at the upscalability and the processing at small scale to evaluate the use of these materials for the subsequent work packages. So I'll try to take you through some of the polyester synthesis that has been done in the project. This, of course, encompasses all the different monomers that have been produced in the first work packages, and therefore we can't talk about all of them. We don't have time for that today, but I'll give you some insight into some of them. And one of them we already heard about in Tanya's presentation, and that's 4-hydroxyphenyl acetate, acetic acid, which we use to prepare poly-4-hydroxyphenyl acetic acid, acetate, PHPA. It is not a super well-known monomer, so it is, but it is highly attractive, as Tanya also showed earlier. This pathway enables it as a fully bio-based system, and therefore we were very keen to investigate this throughout the project. HPA has the advantage that it is what you call an AB monomer, so it can be polymerized directly with itself, but hypothetically could also be co-polymerized together with other monomers, but we'll get back to that later on. What is a little bit special for this aromatic building block is that it actually is a liquid crystalline polymer. This is important for its use, and it's also a very specific application of it. But basically, you can see that it retains crystalline behavior throughout a long temperature cycle, even though it is actually a liquid product. And that provides some possibilities for using it in modification schemes to prepare more combinations of PHPA and other polymers. But as the starting point, Tanya mentioned the different processing steps taking place with this. That also means that there was a lot of different variants of synthetic pathways for HPA before we could use it for polymerizations. And what we were actually very keen on investigating for many of these systems has been the purity requirements of the monomers as we get them into the process in Work Package 4. And I'll give you an insight into what that looks like for HPA. Because what is, from our point of view, very interesting here is to understand the link to the specific downstream process and how that impacts the possibility to polymerize these systems. So for HPA, Tanya showed the process before, but if we look at these two plots that you have here, what we can see is that we have the purity of the HPA after different purification processes, different choices of acids for acidification or different process steps in the purification. Essentially, it's the same monomer, but there are a few impurities carried along in the different purification processes, and therefore we were interested in understanding how much that affects the ability to polymerize these things. And what you can see here on the x-axis here is the purity of the system, and out here you can see the molar mass for these. These are not high molar mass polymers, which really doesn't matter for the point that I'm trying to make here. But what you can see is that purity is actually not the decisive factor for the molar mass that we can get from these systems. So we actually are able to use a low purity monomer to produce a polymer in the end. This is highly interesting because, of course, whenever you do additional purification steps, you also reduce the overall yield of the compound. And therefore, it's very interesting if we can use a less pure stream to actually produce new polymers. Of course, if these impurities result in a discoloration of the product, then it becomes less relevant. And you can see on the right-hand side that in some cases, the absorbance curve here on the y-axis indicates how much coloration do you have in the systems. So you can see that when you go really far down in purity, there are compounds in there that would lead to a discoloration of the product. So it's not a free meal, but there are some possibilities in using less stringent purification processes, as you can also see from the green curve here, where increasing the purity from 85% up to almost 100% purity doesn't change much in terms of coloration, and similarly, the same study also doesn't change much in terms of molar mass for these systems. So there is room to use the products at a lower purity than what would otherwise be the case. And this we have done across the different range of monomers that have been achieved or received in work package 4. So in addition to the HPA monomers, we have also received a range of terephthalic acid hydrolysates. These have primarily been produced by acid through enzymatic processes. These can then be mixtures of terephthalic acid and salts. It can also be other residues from buffers and other things that are in these systems. And what we were trying to do here was to co-polymerize these into intermediates, and intermediates that we could then purify. Again, considering the possibility to use a less pure starting material. Of course, we can always purify the starting material even further and then get an effective polymerization. But essentially, again, if we can do this at a slightly lower purity requirement in the first place, we can optimize the overall yield of the hydrolysates that are achieved. This can be through oligomers. It could also be bis-hydroxyethyl esters, BHET, which is also a common starting material for polyesterifications. If we start with the hydrolysates, so taking the upper part of this diagram first, using that to produce intermediates can be done thermally, but what we have also done here is investigate this through microwave chemistry. Microwave chemistry gives us the ability to screen faster. We don't need to use days to polymerize these systems. We can actually do this within hours, and that therefore permits us to investigate the use of different catalysts so that we can also investigate less harmful types of catalysts. Very often antimony catalysts are used for these polymerizations, and it would be highly attractive if we can transition that into, for instance, titanium catalysts or zinc catalysts instead of the tin catalysts that are also often used as an alternative here. I don't want to go into the details of the different systems, but what you can see is that we can investigate different catalysts, and we can see how that affects the distribution of the different products. If we go out here on the right-hand side, this is the size exclusion chromatography that you can see. And what is very interesting here for the hydrolysates for these is that the titanium catalyst is actually superior in making new polymers compared to the industry standard, which is the antimony catalyst. The color of these polymers is not always perfect in terms of new polymers. So you can see here in some cases we get a heavy discoloration from some of these, and we believe that this is related to oxidative coupling of some of these systems. But with the higher purity of the starting materials, we are able to convert these into polymers. If we then, on the other hand, look at the bottom part here, this is one of the other monomers that were achieved from the earlier work packages, where instead of acid, this is work done at Aachen, where they have hydrolyzed the PET and produced BHET as a monomer for further polymerization into PET. So we have done exactly the same study under the same target, in trying to find a good intermediate that we can use for further purification. And if we look at the BHET data instead, we can similarly screen across different choices of catalysts. We can also see that that has different impact in terms of coloration. But what is maybe more interesting is if we go in here on the SEC data and we compare the titanium data, which you can see here, and the antimony data, which you can see right above. And compared to what we saw from the terephthalic acid hydrolysates, we actually see here that the antimony catalyst is better for the PHET. So there are a preference for the different catalysts, where one is more suitable for transesterification, whereas the other one is more suitable for direct polyesterification from these systems. Also, lower purity monomers were investigated. Here, it seems that we do only get a little additional color, and that seems to be directly related to the discoloration in the monomers when they're produced. So if we can get rid of the excess color from the monomer, it seems to be what coloration we have mainly for the monomers. The titanium in this case gives a heavy discoloration for these systems. So the microwave oven, we are able to screen faster across different types of catalysts to get an evaluation of their usefulness for working with these, both in less pure streams, but also in more purified monomers for making new polymers based on these degraded monomer profiles. For the polymerization itself, there's also been an extensive study conducted in trying to substitute more harmful tin-based catalysts, where particularly the group at Aachen has been working heavily on using non-toxic iron and zinc catalysts for a fast ring opening polymerization of lactide. So if you noticed on the former slides, there was also a study in depolymerization of PLA. This leads to ultimately a lactide that we would like to repolymerize into PLA. And the study here has then looked into designing these new types of iron catalysts, looking at different types of ligands for the catalyst in order to be able to obtain an efficient polymerization process with these much more benign catalysts. And particularly add-on for this is to then upscale the production of these catalysts and then also look at them for use in reactive extrusion, which has been done in collaboration with AMPLAS, which I'll get back to later in this presentation. These different types of iron catalysts are prepared relatively straightforwardly. There's been a range of these catalysts investigated, so more than 15 different compounds, and it's clear that there is a very dramatic increase in activity for these systems, and they are highly active. Multiple of these have already been published, and as I said, one of them has been scaled up and tested for continuous production in reactive extrusion. Another element in using other advanced polymerization methods has been to use enzymatic processes. If we look broadly across different feed compounds, there are a lot of different monomers available, both from a bio-based origin as well as from the different feed streams that we looked at earlier. And many of these can be polymerized not using chemical catalysts, but using enzymes instead, in order to obtain highly functional polyesters that could be considered alternatives to PET, but also could possibly have different other applications that we also have been looking into. One of the elements here is that enzymatic polymerization also often takes place in more harmful choices of solvents, and therefore an element here has also been the use of green solvents as replacements of diphenyl ether, which is a common solvent for these systems. And the work at ACID has looked into the development of the use of styrene and the development of Signet 2, 4, and 5, as you can see them here, and how that reflects their use in polymerizations for these low molar mass polyesters. The polyesters that have been produced here span a broad range. We can see and recognize maybe the FDCA building block that is also produced in the project. We have different adipic acid building blocks. There are other segments in here as well. Across this broad range of oligo polyesters. These have been evaluated as additives, which is a target for the second task of the project. These additives have been evaluated in PHB and also in different of the other PHA analogs that Tanya mentioned in her presentation. An interesting aspect of these polyesters is that they have a drastic influence on the degree of crystallinity in the bacterial polyesters, but also that they affect the rate of crystallization, which is important if we consider applications in, for instance, injection molding and other processing techniques where we don't have a lot of time for crystallization to develop. This is extremely important if we want to tailor the properties of these material and suppress some of the post-crystallization that is often present in PHA systems. The next part that I will touch on is the ecopolymers that you saw Felicia presenting some of the results from earlier. So this is one of those cases where we kind of need to make the polymer first, but then we need to investigate the impact in the earlier work package to see the impacts on the enzyme properties. But this part of the work package focused specifically on making more easily recyclable polymers that could be recycled using the processes from work package 2. This has covered a broader range of interesting building blocks. It has been looking into use of hydrolysates from polyethylene. It has been using different types of linkers to make a batch polymer system where the entire system becomes more degradable. But what we found as particularly interesting are these PHPA polymers that we found to have this very nice aromatic structure, but also a very fast degradation under mild hydrolytic conditions. And if we compare them in the plot that you can see here to PLA, we can see that PHPA degrades rapidly compared to PLA. And if we incorporate it together with PLA, we get an even more drastic effect in terms of weight loss for these systems. So this is a very attractive system for obtaining a higher degradability of these. If we then incorporate the synthesis of this, we can exploit the liquid crystalline behavior to do a copolymerization or transesterification with PLA, incorporating PHPA into PLA. And if we then take this and blend it into PLA, we have a possibility to obtain a range of blend compositions that actually also show a really interesting hydrolytic profile. So what we can see is that if we just blend these copolymers into PLA, only with 3, 5, and 10% of the PHPA-based block copolymer, we get a dramatic increase in weight loss for these under hydrolytic conditions. What is very interesting here is that this does not, to a very significant effect, affect the material's mechanical properties. So essentially, we have a PLA that has a PLA property, but it is much more rapidly degradable. And as Felicia showed, it is also more rapidly degradable using enzymatic conditions. Similarly, we also investigated PCl and PETG that also retain their mechanical properties. And the last part of this study is still being completed together with the partners in work package 2, as Felicia also mentioned. The last part that I just want to touch upon is the bringing of these different polymer systems towards processability. And this has been a task carried by EMPLAS for all the different systems, where they have done a compounding of different additives. For instance, the P5 has been evaluated as an additive in commercial PHB. They have tested how some of the PHAs produced by bioplastic, how they act together with the commercial PHB in combination with the additive P5, and also in a lot of different other combinations, but we can't go into all the different subsets. But essentially, they've been evaluating how these preliminary materials, additives, can be tailored so that they can be part of a compound that can then be forwarded to work package 6 for further testing under industrial settings. Finally, I just want to touch on the reactive extrusion of the lactide part, where these new iron catalysts from Aachen was tested in collaboration with EMPLAS, where they looked into ring opening polymerization of the lactide under continuous conditions, doing tests to see what kind of limitations are available. This took place through design of experiment studies, where a range of different combinations of conditions were evaluated, looking into the highest efficiency of the catalyst, but also the optimal polymerization conditions for these systems. And you can see the ratio of catalyst to in the system directly reflects on how much polymer is actually achieved. But what is the take-home message from this is that it is a highly active catalyst that is able to produce PLA under continuous processes with relatively little excess lactide being present in the system. So it's a way to scale the process to make it economically a bit more feasible. It makes a much faster polymerization, what is otherwise possible through ring opening polymerization, and therefore also lends its way to supporting this bio-based transition. So if we should just highlight the main outcomes of the project, we can see that we have valorization of different monomers at different purity levels. We can get faster screening done for these systems. We have looked into benign catalysts that are favorable both for condensation polymerization and ring opening polymerization. There is a range of new additives that have been developed and tested for bacterial polyesters. We have also identified a pathway for increasing biodegradation for some of these classical polyester systems, which is currently being evaluated. And some of these more useful candidates have been transferred for upscaling and testing in work package 6. In addition to this, of course, there are a range of publications both being drafted and already available through publications, but Pablo already shared the link for the publications earlier, so you can see that in the chat if you want to have a closer look. But otherwise, we're also open to take questions.
Thank you so much, Anders. So I keep encouraging the audience to enter their question, to read it all at the end of the presentations. I think now we can jump to the next presentation conducted by Georgios Murgas, which is about scale up and manufacturing.
Yep. Let me. Can you see my screen?
Yes, you just need to put in presentation mode. Yes, now we can see full screen.
Yeah, thank you from my side. Thank you to the when you made it to this point. We try to show you where we are. I had a problem. Can you hear me?
Yes, I can, Georgios. Well, now I think it's frozen.
What we are doing and how we proceed.
Sorry to interrupt you, Georgios, because there was like something disconnect you need to share a screen again.
Sorry, I have some, sorry.
We lost the connection for 1 second.
Yeah. Okay.
We can't hear you, and we see if
You
it's
see the
easy.
presentation?
Yes, but not in full mode.
Wait a minute, sorry.
If it's easier for you, I can share my screen.
You see it now?
Yes, now we can see it.
Yeah, thank you very much. Sorry for the problems here.
No problem.
As I mentioned, my name is Georgios Murgas. I'm a researcher and the project manager of the Tecnaro GmbH. We are here at the work package 6. So we try here to show you what we have done with the materials, which we received from the former work packages, especially from work package 4. As a manufacturer, it is very important for us to show what we can do with this. We have to go into industrial applications because, of course, we want to earn money. And if you use these building blocks or the polymers and you can somehow incorporate it in formulations that work in technical applications, you can at first show that you are closing the loop. And the second thing is that the material is getting even cheaper and cheaper. So you enforce that these biomaterials can go into the market and into applications. For us, for the Uplift project, it was important to show that we can go into, that we can demonstrate that the things that we are producing here go into have industrial relevance. And for that point, we choose the industrial packaging for the food and beverage industry because, as Professor Cristiano and others mentioned, the most of the waste which is produced is food and drink beverage because it's the life cycle is very, very short. You use it, you open it, and you throw it away. So to get their materials again by depolymerisation and synthesis, chemo-enzymatic synthesis, and to get again polymers and additives, you will show that you can close the loop. It is very important for that. So Work Package 6, we were 2 manufacturers, 2 compounders. The one partner is from Croatia, and it's BioMe, and to show that we do not produce the same products and have several tasks. BioMe is a compounder for flexible packaging. Their main work is was the flexible film production, and you can go to their website, see that they are a great company from Croatia. They do a lot of biodegradable materials. And their part was the flexible packaging, and we divided our part for rigid packaging. For this method, we use the flat sheet extrusion or the extrusion blow molding. So these are 2 different approaches to 2 different products. And so we had on the one side the flexible packaging, on the other side the rigid packaging. The main tasks were formulation development. We have to see in which formulation we can go with the materials that we get from the firmer work packages. We had to scale up these formulations and to see if they are working, how we want to do it. We have to make material characterizations to see if they are processable the way that we want, or do they have material properties which are not good enough or good enough for this application. And the last point is, of course, we have to validate it if they can go for food and drink packaging applications. On our talk here, on my talk, I will talk only about the rigid packaging because it would be too much. And I will focus only on the Tecnaro part, but you can also go and visit BioMe, the site. It's a very good site, and I wanted to show you our second partner. Of course, there were other partners also involved, but we were the 2 main manufacturers. And before we go to manufacturing, I want to introduce you a little bit Tecnaro, because some of our viewers or listeners do not know Tecnaro. Tecnaro is a SME. We have 45 co-workers now, and we produce biocompounds. Everything which is bio-based, from wax to polymers like PLA, polyesters, cellulose, wood fibers, everything is what is really bio-based. We try to compound it and to make biocompounds which can replace commercially available petroleum-based materials or plastic materials. For that, the material properties have to fit. And we have here also a research and development department where I work here in, to have a collaboration also with the customers to see if we can do their products better, but we also participated in projects. As you can see, we do it now for 26 years, and we do it, I would say, well, because we have won a lot of awards for our products. We are located at the south of Germany, here in Ilsfeld, and normally this area is known for their automotive industry, not for the biopolymer compounds, but we try to change it. And if you are interested, you can go to our website and see about the company profile. So in this project, as you have seen in the introduction slide, we were at the end of the project. So we had to balance a little bit the problem that we have to receive material from firmer work packages and to start working on our work package 2. So one of the main part is to develop formulations for this rigid packaging. And for that, Tecnaro, as a compounder, knows how different biomolecules behave and how they interact between other. We have in our we have a polymer database of 5,000 recipes, and we know exactly how the different polymers additives react if you vary the components. The questions that we have to put to ourselves, you have to go to which application you want. We know that we want to go in food, drink packaging. We had to choose the base polymer, because the base polymer, it should be available. It should have the right properties like molecular weight, rheology parameters. We have to choose the processing method. For us, it was the flat sheet extrusion. And we had to we have to think about, should our compound should be biodegradable or not? For other further applications, would it be easier to do it? Because it's a single-use plastic sometimes, you open it, you throw it away. Makes it sense to make it biodegradable. This is a point that we had also to think about it. And of course, cost effective. We have to create compounds which should compete with petroleum-based polymer or plastic materials. So the main focus is also to produce cost-effective compounds. And all these thoughts go into the formulation development. In our case, we decided to use the recipe here down with PLA as a basic polymer, because PLA is the most used polymer for industrial applications, since it's industrial compostable and the streams are there, the market is there. And also they have different grades with different molecular weights and properties. So the variety is very, very high. In this formulation that we developed, we put also PBS in. PBS is also an aliphatic polyester. It makes the compounds biodegradable. And this was one thought that why we incorporated it also in, because we thought maybe we can use this formulation also for a biodegradable type. We have here biostrength. Also, it's an impact modifier. The impact modifier strengthens the compound, and it makes it better for the applications like extrusion. And Licovax is some kind of amide wax, which helps to process the flowability. And talcum is also a filler. So we tried to find the perfect formulation, and this is what comes out in. You see here the percentages of this formulation, and this was our basic formulation for the flat sheet extrusion. We call this a modular principle because the idea is, if you have this formulation, or if you create the formulation, you can put some of them away, or decrease or increase some of the materials and put other ones in. So you have very, very quickly, you can see how the properties change, and you get really good access to the material properties. To get an idea how this works is for the Uplift and only for the flat sheet extrusion and for injection molding for the bottles, we choose 24 formulations. They were selected, they were evaluated, and 4 of them were refined, and of these 4, 2 optimized. So you see, there's a lot of work in selection, refining, and optimization. Here you see how we proceed our main compound. You have here an industrial twin screw extruder. We have it from Comparion. This is a scene where it's in our industry, but it's like in our house. Sorry, that's here in German, but you see here the extruder. We have here twin twin screw extruder. We have here different side feeders and different temperature zones where we heat the material, we mix it. The mixing is available from the screws, from the elements of the screws, and then we have a bath where we cool the strain and granulate it. For this compound that we create here, we use the temperature profile of PLA because it was the main component of the compound, and from this all the components, it has the highest melting point. So the mixing was very, very good. And you see here the different zones and the throughput of the extruder, which was 200 kilograms per hour, which is our smallest extruder. Normally we have extruders with 500 and 1,000 kilograms per hour, but this was our smallest one. And here you see exactly this situation here where the strains comes out from the die, and it's getting cut and it's granulated. I wanted to show you also a slide because this is a very good example how the good collaboration in the Uplift project was, and where the differences is sometimes from the lab scale into the industrial scale. We had material, we had the polyhydroxyalkanoate, the octanoate, sorry. Tanya mentioned that it's polyhydroxyalkanoate, aliphatic polyester. And in our case, we were not able to process it because, as you can see here, it stick together. We don't know exactly until now why they stick together, but it was not able for us to put it in our feeders and to process it. AIM+ as a partner also in this Work Package 6 take this material and find a very good solution to compound it, to mill it. They cool it down with liquid nitrogen, and they mix it, they granulate it, and so we get this granulate from our partners. This shows also the difference that some partners are very good equipped here, and the industrial partners don't have the opportunity, for example, to cool it down with nitrogen. It is too expensive, but we find here a very, very good solution for a problem that was not able for us to solve it. Yeah, but at the end, we get this granulate from AIM+, and we were able to compound it also in our formula. After compounding, what we are doing is we test the materials. This is our machine where we produce this plastic testaments, the testing bones, and we get the analytic results. For us, as a manufacturer, it's important to see quickly how the material properties change and if we can process it for the applications that we want. Here you see the applications for the flat extrusion that we are made. These were the components of our partners, the polyhydroxyoctanoate and the hydroxyphenyl acetic acid. We put that here in, and you can see here that the incorporation of the materials don't impact the material properties. One of the most interesting analytic results for here are the young modulus here. We see that it lost a little bit of its stiffness. It's becoming more flexible. The second thing is that the tensile strength at break. We will see that this material is more stretchable. It's more flexible. And so for the flat extrusion, this is a very, very good sign because you don't want your material to be too stiff. The second most important part is here the rheological properties, because the MVR, the melt volume rate, shows us if it's processable or not. And for the extrusion type, we need smaller values. And we see the incorporation of both components decreased the MVR value, which is very, very good. These were the formulas that we produced for the flat sheet extrusion, and we did the same for injection types, because the bottle production, it was an idea to make bottles by injection molding, and so we created also these two recipes. And you see here again the components of our partners compounded in our basic compound that we developed. And here are again the analytic data. And you see here also the young modulus remains, in one case it's getting a little bit higher. Here it stays the same, but the main result is that in comparison of the materials don't impact the compound properties. One thing that was not so good for us was the melt volume rate here, because we go from an injection type material to an extrusion type. So the material is getting harder to process. So it took much more time to use this material in the injection molding. We have also to test this material, but you can see here, we have to see if this will be working. We take this material from the flat sheet extrusion that was developed and tried now to produce sheets with a flat sheet extrusion, and you can see here the results. The most part that was spent here was finding the right parameters, because if you have different temperatures on the rollers of the calendar, or of the draw off speed of the calendars is not good. You have various thicknesses of the films, and sometimes you have problems with the surface, or you get also defects on the surface. So here, finding the right parameters was a challenge, but at least we can say that the incomparison in the compound was successful, and we were able to produce films, flat sheets, with film thicknesses to 250 micrometers. We have to see that if we go to thinner walls, we have cracks, but at least at this point here with 250 micrometers, sorry, it works very, very well. With this material, we went down and make a thermoforming process. And for this case, we produced this food tray. You see here, we had only 10 sheets or 5 sheets, and we produced 8 of these food trays. But the food trays look very, very good. If we go to thinner walls, as you can see it here, between 75 micrometers and 50 micrometers, this leads to more unstable shells, and they become softer and therefore more malleable. So we found here that this thickness is the best, and the product that we produced here as a demonstrator looks very, very promising. Of course, we have to check and to compare it with actually using food trays, but it looks very, very promising. A second application that we did, or we tried with this extrusion type, is we try to produce bottles by extrusion blow molding, and we get a good bottle here. It has some defects, but the quality of the material is very, very good. So here we have to adjust some processing parameters, because you can see here, some wall defects, or here some scratches on the surface, but the processing is working. The bottle is okay, but the process has to be a little bit adjusted so to get a better quality of the bottles. But also this process was successful. So at the end, what did I show you, or what can we take from this here, is that we created formulations for the rigid packaging and for the injection molding, which were iteratively adapted, and the materials that we get from the work packages 4 are very good incorporated in these formulations, and they are working very, very good for the flat sheet extrusion or for the cast sheet extrusion. The last optimization of the bottle, the process must be optimized, but the transfer was very successful for this 2 applications. Of course, we would scale up this also, but our work package is still running, so some investigations and tests are still running, and I will close with that. And thank you to the partners, thank you to you, and we are open for questions.
Thank you so much, Georges, for showing us all these technical applications and examples. As I said, let's leave the questions for the end of the webinar, and I will give the floor now to Pablo Ariño.
Yeah, thank you so much, Pablo. Let me share my screen. Can you see it?
Yes, we can.
That's great. Thank you so much, Pablo. And well, good morning, everyone, once again. This is Pablo Ariño Aguilar, Business Developer Manager at Sustainable Innovations, and I'm very excited and honored to conclude this final events presentation by taking a look at this final presentation that is going to be about how Uplift different outcomes are aiming to tackle and reshape the plastic packaging industry. So we will explore different market insights, innovations, and opportunities that are setting the stage for more sustainable future. How have we done this? I'm very pleased to introduce and encourage you to look at our website with where different outcomes are published and are available to the general audience, which are mainly a white paper that has been settled in an ready to be look at it at the webpage, which is entitled Pioneering Sustainable Solutions for Plastic Packaging in the Food and Drink Industry, but also as sectoral roadmaps. So these outputs are aiming to provide different or actionable strategies for industry stakeholders to transition towards sustainability. So once again, I encourage you to look at them and try to take advantage of it. The main aim of this presentation is to go to this white paper into detail and explain what has been the Uplift ambition, what are the main innovation that has been developed and before introduced in a technical way, but how this can disrupt the food and drink packaging industry. So moving forward, starting with what's Uplift's ambition. So we can set and define the white paper that Uplift is leading a revolutionary shift in recycling by converting complex plastic waste into renewable polymers to mitigate global pollution, directly addressing the pressing issue of this global pollution, which is something to be remarkable. So our main ambition is to redesign this food and drink packaging value chain by introducing two groundbreaking pillars, the chemo-enzymatic recycling and the eco-design materials. We will look at it later on detail, but these are our mainly the two main innovations that are driving the shift that Uplift is aiming to tackle. Well, once again, this disruptive approach is committed to backing up the transition of the plastic packaging sector and achieving the following ambitious goals at each different step of the value chains. These include the depolymerisation for infinite recycling, also the purification of monomers, fermentation of bio-based building blocks, the different polymers innovations, and also enhanced packaging life cycles. All of these different value chains stages have been previously analyzed by my colleagues' different work packages and showcase that Uplift is committed to tackle and deliver different solutions for each of the different actors or stages at the value chain. To achieve this, Uplift is focusing on three key steps. The first step is combining the enzymatic depolymerisation of end-of-life plastic waste with different bio-based building blocks. Afterwards, integrating the biochemical upcycling technologies, and finally, develop the eco-design strategies to improve the recyclability. Through these different innovations, Uplift is committed and proud to develop and setting new standards for sustainability in the plastic packaging industry, providing feasible solution, as said before by my colleagues, for long-term environmental impact. So right now we are going to explore and discuss about the main the two pillars that are being the back of the Uplift solutions, the two main innovations. From one side, the Uplift project is envisioning or is looking at introduce a set of different innovations that will shape this plastic packaging industry and identifying the bottlenecks in both design and recycling practices. So Uplift wants to tackle this challenge by including both recyclable and traditionally considered unrecyclable strategies or categories and focusing on two main objectives. So what we have been developed in these two slides are how the different key technical outcomes can be gathered and captured to tackle these two main innovations. Looking at the first innovation, the bio-upcycling of mixed plastic waste by coupling of enzymatic depolymerisation with fermentation of bio-based building blocks. So activities developed in Work Package 2 and 3, we can set as a final guidance that novel biochemical routes to depolymerize efficiently the plastic packaging waste that has been streamed from different industry players can be coupled with renewable building blocks obtained by fermentation of the bio-based feedstocks of plastic hydrolysates. And that's a strategy, that new approach will enable to upcycle them into high quality polymers for more carbon neutral packaging with improved properties. So we can say that Uplift disrupt the current stage of the art by this innovative project that has been captured before. That will not only impact a broader range of different plastic materials, but also increase the quality and value, and eventually complying with several regulations that the food and drink industry requires to avoid any kind of polluting substance that can be that might arise in an alternative mechanical recycling process. So there are 6 different outcomes from different partners that the partners have been working it to provide a feasible solution for these first main innovations, which are the development of a platform for treatment, degradation, and purification of monomers. Also, the activities regarding by Albor and ACIP about the scalable enzymatic and or thermophilic microbial depolymerization processes. Activities regarding the fermentation work packages regarding the efficient microbial production method for fermentation building blocks, but also developing a microbial production of building block in a consolidated bioprocesses. Also, to develop feasible routes for TA and EG to FDCA and TA and EG to PHB, and also developing the multi-layer packaging recycling. So all these different outcomes will hit the different target consumers that can be interested into the innovation that the Uplift project is delivering. And the other pillar, the other solution, it's the eco-design for easily recyclable ecopolymers. As said and explained in detail in BP4 explanation or presentation, we define an eco-design principles to develop these novel circular and renewable value chains for the food and drink packaging by creating these new recyclable polymers, ensuring an easier end of life and make it more recyclable. This Uplift innovation will allow to close in the cycle by saving more of carbon from plastics, keeping the material in the loop. And therefore, we can say that Uplift will exploit its technological outcomes to leverage the competitive advantage in order to maximize the percentage of the recycled plastics feasible to integrate once again in the manufacturing chains. And eventually provide a higher recyclability features for the eco-design materials. These are the 4 main outcomes that have been developed to provide and enable to Uplift partners to tackle and achieve these innovations. Once the innovations are explained, it's time to match them with the main market drivers that are shaping the different plastic packaging industry. So I'm pleased to introduce some relevant information about the 3 key aspects that Uplift is tackling, such as the bioplastics, but also the recycled plastic market and the food and drink packaging industry. All this information can be found at the white paper. So once again, if you want to look at it in detail and check how the Uplift innovation are delivering and tackling the different industry drivers and how they can provide to make it more sustainable food and drink packaging, please look at the white paper available at the webpage. So just a couple of at a glance details about the bioplastics market that we can say that it's undergoing a remarkable transformation, because even though that currently bioplastic only represent about 0.5 of more than 400 million tons of plastic produced annually, the market is experiencing a significantly growth market potential, with production capacities for bioplastic to be projected to reach an estimation by 2028 of around 7.43 million tons. So that's definitely something to be look at it. And bioplastic, we can say that are used for increasing the variety of application, from packaging and consumer products to also electronic, automotive, and textiles application, as said before at Christian's presentation. But we are able to set that the packaging remains the largest market segment for bioplastic, representing around 43% of the total bioplastics in 2023. Also, it's remarkable and meaningful to look at the main market drivers shaping the recycled plastic market. We can say that regarding the European plastic production, almost 20% of this production was circular in 2023, which is something that Europe is leading the recycled plastic market. And from this 20%, we can say that 1% it's bio-based or bio attribute, but also the different mechanical recycled application, pre-consumer or post-consumer, are also shaping these statistics. The main applications that of this recycled plastic market are mainly agriculture, but also building and constructions and packaging that is increasing very much. If you can see at the up right part of the slide, we can see that recycling about the plastic waste management is one of the most important evolution, showcasing an increase of 22% from 2018. So things are So things and strategies from the European Commission are properly being working on it, and we hope that this can be set like a groundbreaking for the upcoming or promising new technologies, such as the ones that are being developed in Uplift. The European production it's increased to 58 million tons in 2022. Which is more or less in transition to meet the circularity targets that are aiming to be targeted. And finally, last but not least, the food and drink packaging industry, which represents the 57% of the post-consumer plastic waste collection by application. So it's the largest sector regarding this plastic waste collection. Also, it's remarkable to mention that Belgium, Netherlands, Germany, and Spain are reaching over 50% of recycling rates. So these are the countries that are performing better than the other ones, reaching this 50% goal. And regarding the post-consumer plastic waste management, we can say that around 37% of this post-consumer waste is recycled. So we can we can say as a conclusion that there is still something to be done in that way, and that's the reason these innovations are being performed. And to conclude, we can say that plastic packaging waste recycling rates are 60% higher when they are collected separately. So mixed waste collection is still something that needs to be tackled, and solutions are being demanded by the European society. Finally, regarding the different activities and outcomes that have been provided in the Uplift white paper, we can say that we developed a meaningful PESTLE and Porter's 5 forces analysis to showcase, okay, the innovation of Uplift technical developments can be matched within how the industry and how the different agents from the market are demanding new solutions. Regarding the PESTLE, we said that as key main aspects or factors for the political dimension, that governments to increase the environmental impact of plastic waste recognition and conducting different actions such as the Single-Use Plastic Directive and the EU Waste similar regulations, but also the friendly policy framework on the sourcing, labeling, and use of bio-based plastics and the use of biodegradable and compostable plastics that was launched in 2022. The economic side was shaped by the different aspects that have been previously addressed, such as the challenge about the scaling up in the production volumes of these ecopolymers, but in the different scientific publications, this information is being highlighted in order to lead the economies of scales and and setting the opportunities that these ecopolymers can bring to the plastic industry. Of course, the social dimension is something to be into consideration. The eagerness for sustainability, such as the 89% of European citizens thinking about the negative impact that the plastic packagings can bring. Also, concerns persist about the affordability of these bioplastics or ecopolymers. And also, they highlight that there is a need for information and labeling. So insufficient information on recycling procedures are being tackled, and therefore activities such as the standardization are being needed. The technological side is being shaped by the biochemical recycling through this plastic biorefinery approach, as explained before, the eco-design plastic packaging, and the multi-layer packaging. So these three dimensions of the Uplift shape the technological dimension for this analysis. Also, the environmental, it's something that it's very significant. Therefore, an LCA assessment has been done within this project and detect the main hotspot at the plastic losses to the environmental and the greenhouse gas emissions linked to the processing of fossil-based raw materials and mismanagement of plastic waste. Finally, the legal framework should be also analyzed, and it's been drawn the different legal different directives and laws that are shaping this industry. And finally, to conclude my presentation, also pleased to showcase that the Porter's 5 forces analysis has been done by outlining the different aspects that can shape the innovations of Uplift. So, for instance, we analyze the threat of new entrants, leveling as moderate because there are high entry barriers due to the capital-intensive R&D technologies and demanding advanced technological knowledge sectors. The different bargaining power, both suppliers and buyers, has been analyzed. The suppliers are considered low due to the limited numbers of suppliers with high switching cost, but Uplift partners can harness or take advantage of these established partnerships and key agreements with the value chains. But also the bargaining power of buyers, it's considered as high due to there are the significant market players to influence, but large-scale piloting activities are expected to be deployed, and also the interest of our members from the advisory board is something that can shape or mitigate this high level of power of buyers. Finally, the rival among existing competitors is considered high due to this. There is a large number of players in the bio-based market with a very limited production, but it's expected to showcase a high growth potential in the pipeline. And the different substitutive products is set as moderate due to the mechanical and chemical recycling strategies might be more mature, but they represent significant drawbacks, so Uplift can take advantage of this situation. Finally, conclusion and way forward, we would like to showcase and encourage the different viewers or attendees of this presentation to look at the main innovation that are being uploaded and promoted in the Innovation Radar tool from the European Commission. So we encourage to have a look at them and trying to collaborate with different Uplift projects to scale up this solution and accelerate the sustainability goals, and explore the different opportunities such as the tools that have been explained in this presentation, and as well as the link to the innovation radar activities. Finally, as a key takeaways, we can say that the Uplift vision is to revolutionize the plastic packaging industry by introduce this disruptive innovation that will close the loop of plastic recycling and design, and paving the way for sustainable practice across the whole food and drink sector. And also, we expect it to take a market impact by addressing these critical industry challenges. And the development of these new technologies, sectoral roadmaps, and different white papers are going to guide us and the industry towards developing circular solutions. So that's all from my side. Thank you very much. And I'm very pleased to tackle any particular question that may arise. Thank you.
Thank you so much, Pablo, for this insightful presentation. So I'm going to start reading and trying to address into the right speaker the question that I have received. So the first one, I think it was, if I'm not wrong, to Alberto. And it says, in your opinion, who are the main drivers who needs to push the strategies at EU level, the implementation of it to make it possible? What is the position of the food industry to implement the Uplift technologies?
Okay, 1 second. Okay, regarding, I think that regarding the food industry, I think that currently the plastic contact in the food industry is opening. For example, as I talk during my presentation, I think that currently is step by step opening to these new models of recycling. Okay, so currently we are considering the traditional recycling technologies, but for example, as I talked in the presentation, take into account the last document, it was presented, I think, in 2022, now is considering new models as could be Uplift as possible recycling strategies for the food industry. So in my opinion, I think that now we are conscious that it's possible to get more recyclable plastic fraction in specific for the food packaging industry, but from novel strategies, in my opinion, focus mainly in chemical and in biological recycling. And in this window, I think that Uplift has an important role, I think.
Thank you, Alberto. So I was copying here all the question that I received. So the next question is, what's the future work to be done for Uplift to go further with the inclusion of that technology in the current world? I don't remember exactly who this question was addressed to, but I don't know if we have any volunteers from the speakers.
Yeah, Pablo, maybe I can start and then the others can complement. So I think the future work of Uplift is we have developed different processes, and we demonstrated that we can scale them up, some of them up to 1,500 liters. But what we need to do to have a real impact and get to the markets is to bring down the costs. And to do that, we need basically to improve the classical efficiencies of these processes, which means we need to improve the yields, the titers, and the productivities in a way that it will be possible to scale this up in an economic way. Because right now we can do it technically, but the costs of the new products would be way too high and not comparable to current market prices. So this will be basically the main challenges for us will be to see at the bottlenecks that we've found right now and go back and do process intensification so that we can produce these materials at better costs, at more comparable costs.
I don't know if someone else wants to contribute.
Maybe I could just quickly say, because Cristiano is addressing the economics of the process, and we do know that biotechnology processes, they're very hard to compare to the price of current petrochemical processes. But that's where incentives and regulations come into play. And if we really want to make changes, I think there has to be a push. Potentially some subsidies also into biotech processes where we can then become competitive and we actually can deliver the solutions at scale.
Great. So the following question is, have you considered perform any LCA studies within the project in order to generate the circularity of plastics? Maybe, Christian, I think you were
Yes.
affirming. Yes.
So the answer is yes. We have a whole work package. We didn't have the time to show the results, but we have a whole work package 5 dedicated to techno-economical analysis, sustainability analysis, LCA, LCC, and also consumer awareness. So we have looked into these topics and we have identified the bottlenecks, also in terms of LCA. And of course, each technology has different bottlenecks. In the case of the chemo-enzymatic depolymerisation, for instance, it was clear that some of the technologies we're using, for instance, to express these enzymes in the lab need to be improved because there are some chemicals that are, for instance, too expensive or are associated to high CO2 emissions. So there's some specific bottlenecks that we have identified. In terms of circularity, I think the overall process has improved the circularity because we're designing for more recyclable materials. But yes, the LCA is one of the decision-making tools that we have used to also decide what process we should scale up. So yes, this was definitely an essential part.
Great. The last question is, you have some great results for the polymerizing polyesters, but what about the polyolefins? It was mentioned as a challenge in work package 1.
Yeah, sorry for speaking all the time. Maybe I can start. This was the task that Aalborg University has been working with quite a bit. So I can tell you some of the results and findings we have obtained. So we have, focusing on polyolefin degradation, for instance, we have obtained relatively, I would say, let's say interesting results from a scientific point of view, but not from a process point of view. So we managed to break down, for instance, 8% of polyethylene, 16% of polypropylene, and 40% of mixed plastic waste. But first of all, these processes were way too slow. This was requiring months. And second of all, what our original aim was not just to break down the polyolefins, but to obtain oligomers that were then easier to repolymerize and obtain more cleavable or more recyclable polyesters. And what we were obtaining was low titer of a mixture of different oligomers that were making the recyclability really, really challenging. And this is why we changed strategy, going from just microbial depolymerization into the valorization and upcycling of the pyrolysis wax. So combining basically the chemical recycling of polyolefins, taking the side stream, which is this pyrolysis wax, and upcycle that. And there we've seen actually quite promising results because these processes are quite fast. We saw that within basically 20 hours, 90% of the polyolefins were converted. And it was also possible after optimization of fed batch feeding strategies to come up to gram scale PHA production out of this. So we changed our original strategy, which was not, I would say, scalable from a process point of view, into this combination with chemical recycling. And this is what we plan actually to work further on, to do process intensification and then scale up, because this seems to be more promising.
And again, I'll jump in because that's part of what I was presenting while it is Cristiano's work. Another fine example where we need to combine different technologies. We combine chemistry, pyrolysis with biological techniques in order to design processes. Yes, we know that enzymatically degrading polyolefins, it is going to be challenging. And I don't see, because of the chemistry of the polymer, that may change. But if we combine biology with chemistry, we can get results, and not just any results, but something that we envisage can be applied on a larger scale.
Great, thank you so much both, Tanya and Cristiano. I think that was all the technical question. I have received another one, which is basically if we are going to share this presentation and the recording of the session. The answer is yes, probably at the end of today or probably tomorrow, it will be available at the Uplift website. So that was basically all the question that we have. However, if you have more or you need to contact any of the project partners, remember that on our website we have a contact form where you can reach us, and I can address all your comments or curiosities to the corresponding partner. That was all from my side. I think we finished on time. I would like to thank all the speakers today and all the attendees that have attended to the sessions of today. I invite you to keep following on social media Uplift, since Giorgio said there are still some pending activities that are still running until the end of February. So we invite you to have a look, a deeper look on social media, because we will be sharing more information and outcomes that the project is still generating. That's all from my side. As I said, we keep in touch. Thank you, all of you, and I hope you have enjoyed this fruitful final event session. So thank you to all the speakers and the attendees.